Today I have with me Dr. Brian Ahern. Dr. Ahern is a physicist with an undergraduate degree from MIT, whose later work focused on exploring BCS theory and superconductivity. In 2012, he issued an in-depth report on nanoscale cold fusion for the Electric Power Research Institute. Earlier this year, the open-source Martin Fleischmann Memorial Project added Brian to their global coalition of researchers and experimentalists who are working to bring an open-source cold fusion solution to the world. He was also a featured lecturer at this year's 2014 MIT L.E.N.R Colloquium, an annual event hosted by Drs. Mitchell Schwartz and Peter Hagelstein. His presentation focused on the relationship between excess heat and nanomagnetism. Brian, thank you for being with me today.
Glad to be here.
So, can you begin by telling us some more about your general background, your credentials, and how you became interested in L.E.N.R or cold fusion?
Back in 1973 to 75, I was getting a master's degree in physics at the University of Vermont, and my thesis advisor was a former student of Brian Josephson, the Nobel Prize winner. He was an experimentalist, and he wanted me to do a thesis to repeat some news out of Warsaw, Poland, where there was an unusual result in superconductivity. In 1973, they found that adding hydrogen to palladium turned the palladium into a superconductor. And when they added deuterium to palladium, it was even a better superconductor. They figured that the Polish made a mistake, so it became my job to verify, that result, adding hydrogen and deuterium to palladium and doing the helium transfers and measuring these transition temperatures that were 9 degrees and 11 degrees Kelvin. So I had to learn to, work in the cryogenic world. And my thesis result was, yes, the Polish were right. We got the exact same result. But that was an anomaly in physics. It was called the inverse isotope effect. All theories said that the deuterium should have had a lower transition temperature, but it had a higher one. But nobody ever solved it. But I worked with palladium, hydrogen, palladium, deuterium long before Pons and Fleischmann. And because it was a master's thesis and I didn't understand a word of it, I wanted to get out of Dodge and never talk about that topic again because I didn't understand a word of it. I did the experiments, but I had no clue about the theory. And then I went off and taught high school for a couple of years, and then I went to MIT for my PhD in material science. And then I ended up working at Rome Laboratory at Hanscom Air Force Base, where in '87 it became my job to understand the new high-temperature superconductors.
When did you first become interested in L.E.N.R?
Probably around 95. When the news hit in '89, I wanted nothing to do with it because that was my thesis topic. And you don't go back to your thesis. It was a painful period, and I didn't want to go back there, so I just ignored it. And not much happened until around 95 when we made a major discovery. I think it's perhaps the biggest discovery in energy in a decade. And it was surprising, the discovery we made, and that reintroduced me to L.E.N.R.
Your focus in college was on superconductivity. Can you provide us with a general explanation of what exactly that is, and what do you find so interesting about it?
Well, MIT professor Keith Johnson was a theoretician who used computers to model atomic systems so that if you had a cluster of atoms that was in the right crystal structure, you could predict what the chemical properties would be just from a very small cluster of atoms. And everybody thought, well, that's garbage in and garbage out, and nobody paid much attention to him. But that's what he did for his career. And in 1980 or so, TDK, a company called TDK, came to him and asked him to help them design new magnets for recording media, and he did that. And in 1974, in the middle of the energy crisis, they asked him to write the seminal article on catalysis for how we can make energy better, and he did that. And in 81, IBM came to him and said, we want you to tell us how to get higher temperature superconductors because we want to make a superconducting supercomputer. And he then modeled known superconductors, and one thing led to another. He figured out the problem completely, and he could explain it to me, and I could explain it to an average high school student. That is what I presented to my laboratory director in 1988, and I told him, do not invest anything in these new high-temperature superconductors, they are inherently bad materials. That is, as you go higher in fission temperature, they become more and more unstable, and you'll never get a working device at very high temperature. And that was indeed correct, and there's never been a device made from those high-temperature superconductors in commerce. 30 years later, that's the story. The higher the temperature, the more unstable, and when you run them at like a high current, they break down.
Why do we call it superconductivity? What's going on in the system that allows for that?
Well, electrons in orbitals around atoms don't get tired. They don't wear down. And in materials like iron or steel, silver, they travel in connected orbitals, but they're not fully connected, so they have to make jumps. And every time they make a jump, that leads to some heating. So most materials have transport of electrons, which is a current. They stay inside connected orbitals. And in high-temperature superconductors, they're fully connected. So when you put a voltage on, the current will flow and it does not dissipate. And that's owing to a subtle feature that Johnson figured out. That's what connects to L.E.N.R.
So in a superconductor, we have like a cooperative state of electrons. Is that basically an okay summary of what's going on in there?
It's actually too concise, and it hides the real meaning. That is, certain materials are inherently unstable. They want to go to a different crystal structure. Iron, for instance, has a Curie temperature. And at the Curie temperature, the crystal structure changes, and it goes to a different structure. That's called a solid-solid phase transformation. And many materials are prone to phase changes. And right at the point where you go from one phase to another, all of a sudden the vibrational modes, they change dramatically. The atoms are normally vibrating randomly and at small amplitude, kind of like little flies buzzing around their wing. But at a phase change, all of a sudden the vibrational modes become very large amplitude and very low frequency. Those are called anharmonic modes. And they're so large in amplitude that the electrons try to move along with the nuclei that are going over large distances. So you have electrons moving over large distances in their orbitals. So in order to have the electrons never leave an orbital, you have to have the orbitals distended, really delocalized. And that's what happens in certain materials that are prone to these phase changes. In 1935, a fellow named Lebedev Landau from Russia met up with Edwin Teller in 1935 in Copenhagen. He handed him a piece of this mineral called perovskite. And he said, "Here, Edwin, you have more money than God. Study this material because it is unusual vibrational modes." And Edwin Teller, academically, he was the world's expert on vibrational modes in materials. That's what he did. So he brought it back to, I think, Berkeley, and his graduate student, Hermann Jahn, and 2 years later they wrote the Jahn-Teller thesis that discussed how very large vibrational modes at low frequency can exist in materials. And that's what Johnson rediscovered, many years later, and found that you can explain the high-temperature superconductors only by having these very large amplitude, low-frequency modes. And the perovskites did that, and that's where the yttrium, barium, copper oxides were. And the higher the temperature, the more prone to phase changes they were. We took that information, and we found a paper from 1953. It wasn't even a paper. It was just a one-page in the Memoirs of a Mathematician. And the mathematician's name was Stanislaw Ulam. That's U-L-A-M. He was at Los Alamos, and they had a computer. They had the only computer west of the Mississippi. It was called Maniac 1, and they gave it a problem to solve. And they just took a linear chain of atoms, not even atoms, just masses connected by ideal springs. And they set them going. This is in a mathematical simulation in the computer. And they wanted to see what would happen to the masses' energies over time. And they found out that they shared the energy equally. They all had roughly the same average vibrational energy. But then Ulam, being the mathematician, said, what if we make a subtle change to the force equation? The force of a spring is F equals a minus Kx. That's Hooke's law. Let's add another term, like plus 1/2 K2x squared. But we'll keep the coefficient really small, so it's just a small change to that harmonic oscillator. And they let the simulation go. This was the first simulation west of the Mississippi. And it astounded them that the energy was not equally shared. It was focused onto a specific location, and it was greatly amplified. They called it energy localization. But that result never made it out of Los Alamos because the Russians detonated a 60 megaton thermonuclear explosion, and everything in Los Alamos was hyper-classified, including the simulation. And it wasn't heard again for 30 more years when everybody had a desktop IBM computer, and anybody could do it. And it was because it appeared in the memoirs of L.E.N.R, this mathematician, came out in the middle 80s. So it said, wow, energy can be shared very, very differently. But there are two conditions. You need to have what's called nonlinear coupling, and then you have to have a countable number. That is, it doesn't work if there's too many masses, and it doesn't work if there's too small a number. So it was unique, mathematical simulation. But I came along in the mid-90s after having worked with Johnson and understanding these delocalized bonds, which are called nonlinear bonds. And we just said the nonlinear coupling between masses is the same as nonlinear bonding. And when we applied that to clusters of atoms, we found that you needed somewhere between 3 up to 12 nanometer clusters, which show this vibrational focusing and very different energetics. And we looked for years collecting thousands of papers. And this thing called energy localization was the biggest deal in science as far as I was concerned, but I couldn't share that information because you can't get the idea across in 15 minutes at a conference. So we continued along looking at energy localization and saying it's a wonderful thing. I don't know how to express it. And then in 2009, I heard of this scientist from Japan named Arata was claiming to get heat energy out of nickel and hydrogen with particles in the 5 to 10 nanometer size regime. But nobody paid attention to him because right after his presentation in Washington, a virile, handsome, strong scientist from the same university got up and said, we did what Arata did and we didn't see anything. Arata was 85 years old in a wheelchair and he couldn't understand him. So who do you pay attention to? Well, the guy who's claiming that nothing happened. So people assume that nothing happened. When I found out about the paper, when it was translated from the Japanese, I went, oh my God, Arata's in the sweet spot. And the guy who failed said, we worked at 20 to 100 nanometers. I go, he's outside the magic range. So I contacted him by email, and over 5 or 6 emails over a month, I convinced him to reprocess his materials into the 5 to 10 nanometer range. He did, and he got the result on the first try, and he reported it at the 20th anniversary on March 23rd in Salt Lake City, that they got the same result as Arata. And it was related to the size of the particles, which only are engaged, I said, between 3 and 12. So you see 5 to 10 is right in the middle of that sweet spot. So there's a new energy expression with materials at that size regime. I'm not saying it's fusion. I'm just saying the energetics are completely different and much more interesting.
So there is some kind of connection between superconductivity, nanoparticles, and then the cold fusion effect.
There is. Conductors have anomalous anharmonic modes. That's how they do a supercurrent. But with nanoparticles, they have the anomalous anharmonic modes. And remember I told you, back in 81, Johnson was tasked to understand ferromagnetism. And he's the only one who ever did. There's no one else on Earth who ever figured out magnetism from an orbital perspective. There is not one person. But Johnson did. And I worked with him, so I just understood his formulas. I couldn't do what he did. But those anharmonic modes that I talked to you about, they're not just large amplitude, low frequency. They're cooperative. They work in concert with each other. So you can get very different behavior. They're called collective modes. And ferromagnetism is already a collective, getting spins to line up. But then you can get all the atoms vibrating to go into like a vortex. And vortices and magnetism were discovered at Max Planck Institute in 2006. They just don't understand these collective orbital effects. So you can get a super ferromagnetism if you divide the materials into down to that size regime. That's what I believe is happening in L.E.N.R. There's surface features or particle dimensions that allow for super ferromagnetism with properties I don't understand.
Even if the nanoparticles can mimic the vibratory character of a superconductor, how is it surviving such high temperatures? Because when we talk of typical superconductors, we're talking about phases of matter that exist at negative 200, 300 degrees Fahrenheit. It's very cold temperatures. So why do we even think that this would be happening at the temperatures that are being applied to a number of systems, including like Rossi's, for example, where they're getting super hot?
Well, superconductivity is limited in temperature because you want to sustain connectivity of orbitals. But for other materials, you don't really care about that. For superconductivity, to have zero resistance, you have to have fully connected orbitals over a certain, well, in order to be fully connected, you have a coherence length. It's like a forgiving regime. But in order to get the supercurrent to flow, you have to have connected orbitals. And as you increase the temperature, you get randomized orbitals. It goes away. Well, you don't care about that for ferromagnetism because you can sustain many hundreds of degrees above that room temperature because it's a different process. There's no limit to where these anharmonic modes quit.
So it's this state, it's this description of Johnson that says this can be happening in these systems. That's the fundamental theoretical foundation that this is based on.
Yes. Atoms that are far away and electrons that are far away, we're trying to bond with the central atom. How do you bond with something that's far away? Well, you can only do that if your orbitals are really distended and distorted. And that's how we made the big discovery. Superferromagnetism can operate at very high temperatures.
But not superconductivity.
Superconductivity, no. There could never, in principle, be a room temperature superconductor. Cannot happen, even for a nanosecond. Because the analogy is, you take a forest, an isolated forest, you can walk all the way around it. How far can you walk into the forest? Halfway. Because once you get to the center, you're walking out. And Johnson's analysis showed that you can only have so much overlap of these orbitals. And once you went too far, you're coming out the other side. So he found the maximum amount of overlap it could have. And you could only get to about a minus 30 degrees centigrade would be the highest transition temperature that could be theoretically possible. But that thing would be so unstable it wouldn't last even a microsecond.
What we have going on instead is a collective mode that is ferromagnetic, but is cooperative in the same sense that superconductivity is cooperative. Now, they're not the same thing, so I shouldn't say the same sense. But
no, it's cooperative. The oscillations are collective, and you can say coordinated, but they break down as the temperature increases. But with a L.E.N.R, the nickel system, you can have ferromagnetism go up to 1,000 degrees.
So when this cooperative mode is entered into, where is the energy coming from? Are we confined by conservation laws within the system, especially if it's not fusion? What is producing the excess heat?
I engaged Donald Hodgson on his view of the universe. He had several articles published in Infinite Energy in 2002 and 2003, and I was one of the editors. And I liked his work. I said, it's the best thing that's done in physics, or it's terrible and it's negligible. I couldn't tell. But I paid to have him come and spend several days with me at my house. He died about a month ago. But his view of the vacuum allows for energy to come like from a 0 point, or however you want to discuss it. I think we have a magnetic interrogation of the vacuum, and that's where I think the energy is coming from.
So these nanomagnetic vortices that you said have only been basically explored for 7-8 years tops are sort of transducing the vacuum energy.
People who are investigating it are not involved in energy. They're all computer people. They're looking for a better computer storage device. So they're not looking at the energetics.
So is the transduction analogy a decent one? Do these act as little transducers? Are they transforming, say, vacuum energy into whatever, heat, current, something?
That is what I think is happening.
Okay. Now that's interesting. So they're only modeling these vortices, they're not actually experimenting with them in systems, and if they are,
they're measuring.
Are they seeing excess heat in those systems? Is there any reason to believe that that's happening?
They're measuring this at the nanoscale. They're just looking at, under an atomic force microscope or something. They haven't applied this to energy in any way.
They're not measuring for heat in these experiments. No. They're not looking for it, so they probably wouldn't notice it.
No, not at all.
But it might be going on, and they just don't notice it.
Right.
Okay. Now, is there some way to test whether this coherent mode is actually being entered into, or is it purely theoretical? I mean, is there some kind of dead giveaway if we were to test a system and say, aha, that is a coherent, connected, ferromagnetic supersystem?
No, I think it's still somewhat speculative, but I have a little write-up that I share called energy localization. And in that, they show a simple system. Imagine a petri dish, made of plastic, and you fill the petri dish with BBs, like little copper balls, you know what BBs are?
Sure.
You put it on a vibrating table and you let it vibrate, and the BBs will be jumbling, and they have amplitude of vibration maybe 3 BBs high. That's the average vibrational mode. But then if you take static charge and put it on the BBs so that they have a little bit of repulsion from one another, that's a non-linear effect. So you couple them non-linearly, and all of a sudden the BBs act collectively. They have vibrational modes that go 30 BBs high, and they repeat indefinitely. They make like volcanoes. And these are inanimate objects that collectively vibrate when they're non-linear coupled. This effect works at all size scales. I mean, it works at galactic scales. People have demonstrated it working with hockey pucks. And the BB one was on the cover of Nature in 1996. They called it Oscillon. But they didn't know how to deal with it because they didn't have the experience with Johnson to know what vibrational modes could do.
Two quick things. I can't help but think about self-organizing systems when I think about quantum coherence or coherent oscillations or syncing of resonances, however you want to term it. And self-organization is, like you just said, you see it everywhere. You see it in galaxies. You see it at the very small scale. It's a very interesting phenomenon. And to see something like that exhibited in an energy system, I think, is a provocative idea to play with and to consider. Because I've always seen L.E.N.R and cold fusion kind of as a chaotic self-organizing system in a sense. So I think you can hypothesize some interesting things that go on in an environment like that. And that's just a novel idea to see the analogy work its way throughout nature. You can apply it to a lot of different models. And that's what attracts me to your model in the one sense. So yes, it's speculative. We don't yet know if these things can transduce energy. That would have to be tested for. But just that general framework, I think, is not a bad one at all. And also, this has been noticed in other systems where you have giant oscillating ions that are producing kind of anomalous energetic effects. So it's not just in cold fusion systems. And you seem to have stumbled across it yourself at some point in your work. I think there's a lot of ways of coming at it as well.
I do, and I'm not trying to be grandstanding, but I've presented this, a half dozen times at conferences. And L.E.N.R worked on this the rest of his life, kept it to himself. He invented a whole topic in physics called chaos theory. Have you heard of that?
Yeah, I've probably read every relevant book on chaos theory for a layman.
L.E.N.R was fascinated by how this thing self-organized itself, and he found the conditions for energy localization. It took him years, but he said, you need a countable number, too many doesn't work, too few doesn't work, and they had to be non-linearly coupled, either mathematically or in chemical systems, non-linearly bonded. And if you did that, you would get these massive vibrational modes. If you saw the picture of the BBs, they were like fountains. Instead of just vibrating at 2 to 3 atomic dimensions, they had 30, 50 dimensions. And the BBs would come so far apart, they would break bonds. So if that was a chemical system, you would have something that could break bonds and reform them 10 to the 12 times per second. And this was a way of, instead of having a temperature-promoted reaction, you had a non-linear vibrational mode that could induce chemical reactions with an incredible efficiency. And then you say, well, who would take advantage of this system? And you say, living systems. At the core of all living systems are enzymes that produce protein. How can they make ordered structures out of random chaos with the second law of thermodynamics? But with these energy localization modes, you can circumvent the second law and you can make ordered structures because the enzymes are all between 5 and 10 nanometers and they have energy localization by anharmonic modes operating. That is the essence of life in terms of how the energetics work. I'm not saying I know any details, but enzymes are highly specific and ridiculously efficient. There's no artificial system that's even got within 0.1% of an enzyme. And they do it with energy localization. And if they were bigger than 15 nanometers, they wouldn't function. And there are no enzymes that have all of their three dimensions above 15 nanometers. So that's where energy evolved on Earth in all living systems. This is the energetic mode. I'm not saying it's good for anything, and that and 395 will get you a latte at Starbucks. But that's how things work. There's never been an answer for, hey, how does nature create order out of chaos? And this is how it does it. It's this energy localization phenomenon.
Right. I think Prigogine won the Nobel Prize for this very phenomenon.
No, he didn't. He won the Nobel Prize for nonlinear thermodynamics. He had no idea about energy localization.
Fair enough. But he was heavily involved in the science and mathematics of nonlinear dynamics. That's certainly important.
Oh, yes. He was, and I agree with you.
Okay, fair enough. So I think we've fleshed out the theory quite a bit. Maybe we can jump real quick to kind of an interesting anecdote. During your lecture at MIT, you told a story of a car battery you witnessed that seemed to demonstrate effects that in ways were beyond belief in terms of making use of the process you described. Could you elaborate a bit more on that?
In 2011, I was working on an EPRI contract with nickel nanopowders adding hydrogen and deuterium, and I was getting good results. I was getting excess heat in every experiment, but not that much, about 100 to 200 milliwatts. But it was continuous. It would keep going forever, but, I wasn't too proud of it. And I said, well, what happens if I would put high voltage pulses through this material? And a fellow from Colorado gave me a virtuoso power supply that could do that. And I hooked it up, and I spent weeks getting ready, and I sent pulses of 1,200 volts, 2,000 of them a second, through my material. And I burnt out the power supply in 15 seconds. And I said, what am I going to do? It's like your television burns out. I can't fix that. So he sent a fellow down to help me named Arthur Manellis. I didn't know who he was. He was, 30 miles away. And he came down and he showed up in a very fancy sports car, Lamborghini. It wasn't a Lamborghini, but something like that. And he said, oh, he can take the parts back and he'd fix it. And he brought it back to my house the next day and we ran it and it burnt out in about a minute. Some progress. He said, let me take it back. All the nano powders, the vacuum pumps, everything to my house. I'll get it running. He was running away with the show, but he's the only one who could fix the power supply. So I showed up at his house just before Labor Day in 2011. And he showed me a car, a Selectria, which was a all-electric car built in Massachusetts in the early 90s. And he was an automobile restorer. And he had restored this one and put in new batteries. And he had a device in the trunk that said, that's powering the car. I go, what are you talking about? Being a physicist, the last thing you want to give up is on the first law of thermodynamics. And he was saying he had a device that was taking energy from the battery, using energy, and putting back more. So it was a perpetual motion machine, which I thought was preposterous, but he wasn't a crazy guy. He was probably the most mechanically talented person I had ever seen. He had restored cars right on the property that were remarkable. And he was retired, and he was just following the work of a guy named Floyd Sweet, and he just was getting something working. Well, I said, well, I don't know. I'm willing to give it a measurement at least. But, he didn't want to give up his car. So the only value I had was, I said, I will test it in your garage, but I will run the car, 4 people in it for 25 miles. We'll park it in the garage. I'll cover it with a tarpaulin. I will nail it to the floor, and I'll put evidence tape around it, and I'll have cameras looking at it, and we'll watch what happens over 24 hours. And we had voltmeters that could take a measurement every second and record it, and then we printed it out. And sure enough, that thing recharged itself over a week. Well, nobody believed that. They say, well, batteries have a way of the voltage going up, so having the voltage go up doesn't really tell you anything. The voltage never increases on a battery if you're loading it with 50 watts of drain. Never happened. But nobody was convinced. So he let me make some more measurements. So I ran a light bulb at 60 watts for 4 days off the battery pack, and the voltage still increased. The most important thing was we put room temperature. But the key parameter ran 5 degrees centigrade colder than the environment. It was the exact opposite of how a transformer should respond. This was the core of the transformer was running cold. And that has never been observed, well, in my lifetime. And that's when we knew we had some new physics. Didn't know how or what, but I knew there was something important. And the reason that Manellas came to my house is because he heard I was looking to put high voltage pulses through nanomagnetic material, and his device was using high voltage pulses surrounding a magnetic material that was made from nanoparticles. So that's why he came to me, and that's why I'm keenly interested in the topic of nanomagnetism. I don't propose to understand it, I'm just saying it's early going.
Very interesting. Like I mentioned in the introduction, you have more recently become an active member of the Martin Fleischmann Memorial Project. Can you give us an overview of what that is exactly and what your specific role will be?
I have a very limited role. They want to repeat some of the stuff that Arata did, and because Rossi is claiming thousands of watts of excess power, they're saying, well, what can we do to get any power out? And I said, well, I'll give you some of my power. And I was only getting 100 to 200 milliwatts. That's a really small number. You know, that's about the power of your wristwatch. It was real, but it was negligible. But I had one experiment that exploded on me, what we call a runaway experiment. That, when I look back in the notes, was not because, it was coincident with me grinding that powder much longer than I had ever done. I just went away to vacation. I left it going for 2 weeks inadvertently. Normally I would grind for 3 days. I ground for 2 weeks. I ran the material, and it blew up right next to my head and came out like a flamethrower. Because when particles that have a huge amount of hydrogen come out and hit the atmosphere, ooh, do they react. So I recovered from the explosion, but I didn't put two and two together until several years later when I went back and saw, oh, that was the one I overground. And the smaller particle dimensions seem to track with other people having events. So I wanted the Martin Fleischmann people to take my powder, regrind it, and see if they get more energy out. That seemed like it was like, could give you 10,000 times more energy. So that's what they're looking to do right now.
Have they had any results, or is it still in process?
No, they haven't got to run it yet. They're doing calibration, so I'd say they're within a couple of weeks.
So what are your general thoughts on the MIT colloquium held earlier this year? Were there any perceived breakthroughs or points of interest worth paying attention to in the future?
Oh, yeah. I think there's a huge Mizuno experiment. Mizuno sent an associate to make the presentation, but they did it with Skype, and he was actively on call. We could ask questions of him, and we could see his face, so that we had a Skype into the community. And Mizuno is very clever, and he is doing experiments where he's got a coefficient of performance of 2. That is, he puts in 80 watts, he's getting out 160 watts. And he showed how he did it. He took nickel wire, and he did a glow discharge for a series of hours, and that took the surface of the nickel and made it fractalize at the nanoscale. And that's all he did. Then he added hydrogen, and he got more heat out. So I liked it because it was nanoscale effect, and that he was getting reasonable numbers. He's getting the best repeatable result we've ever seen in the field. So I was saying, that's huge. And they're planning to have a 1,000-watt device by Thanksgiving. They called it Dorothy, and he showed a picture of it. They've already got it built, and they've already got a 10,000-watt device built. We don't know if it scales. He could put in 80 watts, get out 160, but if he puts in 1,000 watts, he might only get 1,080. You know, that excess might not scale. But if he put two systems side by side, each putting in 80, then he'd get out 160, 160. So we don't know how they're doing it, but very exciting work with nanoscale surface features.
For people who don't know who Mizuno is, he sounds obscure, but actually in the cold fusion community, he's a pretty big figure. He wrote a book, I think in '96, called Transmutation, the Reality of Cold Fusion. He recounted his story and how he went about discovering the phenomenon for himself. And he produced probably one of the most drastic episodes of after-death heat effect ever known. Now, unfortunately, it wasn't being monitored. In fact, he was just trying to kill the experiment. And it kept going, and he kept boiling away water overnight, just tubs of it for days. And I think that in and of itself is just clear evidence, unless they're going to dismiss him as completely either a liar or a completely delusional crazy person that doesn't know when water is boiled away, or that someone's playing a trick on them, which would be equally bizarre. We have this huge heat effect going on. But he was also one of the first to find neutrons and whatnot, so experimentally he's been a big contributor. And I think when he speaks and says he's doing something, I think people should pay attention. So I agree, that's very interesting. Now, I guess if he's maybe building a reactor, or if Martin Fleisch Memorial Project is working towards those ends, or one of the players like Rossi or Brillouin or somebody makes it happen, how do you see the progression and implementation of L.E.N.R unfolding on both a commercial and like a societal scale in the coming decades?
Can I go back to Mizuno for a minute?
Yes, you may.
I just want to tell you, Mizuno in 2005 announced an experiment that he did where he just took deuterium gas and put it in a tube. No special materials at all, just any tube, and he put it in a strong magnetic field, a very strong magnetic field. And he saw bursts of neutrons. Well, I thought that was interesting, so I said, I'm going to repeat that. And at the time, I was kind of a wealthy guy, so, I was like the gentleman scientist. I went to the magnet lab at MIT, and I got the help of the former director, Henry Cohn, and he helped me build a static magnetic system that had a huge magnetic field. And I repeated Mizuno's work, and I got excess neutrons. And I thought it was great, but it wasn't like his. And I couldn't get anybody else to agree to do the experiment because they were afraid of being tied with the brush of cold fusion. I go, this isn't cold fusion. This is just deuterium being disturbed by a magnetic field, and it's a wonderful thing. I had a professor at Boston College who had the magnet that could do it, and I would pay him handsomely to do it, and he refused because he didn't want to be tied with the brush of cold fusion. And I say, it's not cold fusion. We're looking at the stability of deuterium in a magnetic field. So I got those results, but I never published them. And nobody else would take it up. It was easy to do. So Mizuno is important. I see that it's a great opening scene, but heat output is not the signature of L.E.N.R. It's Manelis's electricity in, more electricity out. Heat is a byproduct you don't want to deal with. So I think when they show that the heat works at the kilowatt level, people will say, where's the energy coming from? And the question will be, well, what else can we do? Because Rossi has all the IP. What do we do that's different? What's different is heat is not the primary signature. It's the electromagnetic effects, not just the nanoscale, but the nonlinear scale that by far the most important. So I think it will open the argument to say, we saw it with palladium, we didn't know what it was, but we saw little bits of heat. You couldn't account for it chemically, so we thought it was nuclear, but it's not nuclear, it's electromagnetic. And we don't understand electromagnetism, but Henry Cohn, I think I told you, he helped me do the Mizuno experiment, and he was long retired, but he told me that at one time he believed he knew more about magnetism than anybody in the world. He says that's not true anymore because he's an old man, but he says, we were just scratching the surface. There's so much we don't know. I really took that to heart from a guy who, had been through the wars. He died about 3 years ago at 86. He admitted that he was in the lead and there was so much they didn't know.
We've been talking for almost an hour, so maybe we'll start wrapping up a little bit. Before we go, would you care to leave us with any closing thoughts or comments or anything that you're working towards or working on?
Well, I'm not doing much right now. I'm waiting for the Rossi report, which isn't really a Rossi report. It's something that was funded by L.L.N.R. L.L.N.R is the Swedish equivalent of the Electric Power Research Institute in this country. And I understand that they put out €500,000 to do better tests of the Rossi stuff. But Rossi couldn't be anywhere near the material, and they had to publish the results, whether they were good, bad, or indifferent. They couldn't just keep them to themselves. They wouldn't pay for the test unless they agreed to publication. And Rossi agreed to that. But he says he doesn't know the results. We all don't know the results. If it comes out with a coefficient of performance on the scale of 2 at a kilowatt, I think that's a gold rush number. But if it comes out below 1.4, people will say it's in the noise level. It'll be distressing.
I'm also looking forward to the report. Anything's possible, and it might come out and be negative, and so be it. But at the same time, I'm leaning towards it being positive in that, yes, there might have been other factors involved, but they seem to be going through the trouble of analyzing the ash or the powder. So why bother if you didn't see excess heat? Why not just publish, say, we didn't see anything, let's just get this off our back and move on? But they seem to be going through the process of having that tested, so I'm at least hopeful. I'm more hopeful than I am neutral, based on that. But we'll see. The first tests were convincing to me personally until something else comes out to prove otherwise. Now, a lot of people want to make a lot of conclusions about what might have been happening in those tests and what have you. But I think some of the explanations for conspiracy theories about how it was all a fake are as difficult to believe as that it was actually working, because we know L.E.N.R is real. I mean, it's beyond a question of a doubt experimentally. We're not manifesting fairies in a lab. Like a skeptic would say, okay, well, we don't even know the effect is real. Of course we do. So if we know it's real, is it really so absurd that it's happening, that someone finally stumbled across a way to do it? I don't think so, but we'll see. I'm hopeful, but I'm willing to accept if it doesn't work out, because I think the effect is real one way or another, and whether Rossi does it or somebody else does it, I don't care, and I think someone will do it eventually, and we'll see.
I got to tell you, I believe in a group delusion. I believe you can hypnotize a whole room. And I worry, and I ask people, am I delusional? Did I just want this so badly that I did things? And the good news is, I didn't even know how to make the measurements. I didn't even know how to set up the voltmeters. Other people did that for me. Then they downloaded the material and they printed it out. So I would have cheated. That is, my subconscious would have done it, whatever it took to do it. But, hey, it wasn't me doing it. That's why I really like the data. And my data, which I did where I was getting energy out of the errata-like powders, routine, it worked every time. It just was not remarkable.
Right.
So I do believe if you get the right size regime and some things going, like the right catalyst, that it can be 10,000 times better. And I think Rossi might have stumbled on it.
I concur. I don't think he knows what's going on at all. I think he has ideas and he's pieced it together in a way like an engineer would, and he's very clever if he's getting what he says he's getting and we think he's getting. And so he's able to do that just because he's a clever engineer, not because he necessarily understands the theory behind everything. So I'm not looking to him for theory, and honestly, I'm not even looking to many of the theorists for theory, because a lot of it's all up in the air at this point. I'm looking what are the commonalities, what works, what doesn't. We just have to be honest about the evidence and find out what works. So, Brian, thank you for being with me today. I really appreciate it.